In this video, I will explain the nature and the origin of spin-orbit interaction. Additionally, I will detail the innovative measurement method for spin-orbit interaction that I developed around 5 years ago. The spin-orbit interaction is one of fundamental forces in physics, and it impacts various scientific fields. A comprehensive understanding of its fundamentals and features is crucial to clarify a wide array of effects and peculiarities in physics. This video is based on my model of spin-orbit interaction, which I have been developing over the past decade. The model has overwhelming support from a variety of experimental measurements. Spin-orbit interaction is an effect that describes a magnetic field originating from the movement of electron in an electrical field. This magnetic field, known as the magnetic field of spin-orbit interaction, shown here, aligns the electron's spin along its own direction. It has a relativistic origin. Even if in static coordinate systems there is only an electrical field, this one, and the magnetic field is absent, a moving electron experiences a magnetic field, this. This occurs due to the relativistic transformation between electric and magnetic fields, components of a unified electromagnetic field. It is important to emphasize that the magnetic field of spin-orbit interaction, this one, is an absolutely real magnetic field, and it is the only parameter which characterizes the spin-orbit interaction. The spin-orbit interaction shares a close relationship with the Lorentz force or Hall effect. The Lorentz force emerges when an electron moves within magnetic field. This force arises from the same relativistic principle. In static magnetic field, shown here, the electron experiences an electrical field in the coordinate system moving with it. This electrical field, shown here, interacts with the electron charge, forcing the electron to change its trajectory. I would like to clarify a common misconception that spin-orbit interaction is quantum mechanical effect. Contrary to this belief, it is a relativistic effect, but not a quantum mechanical effect. This misconception arises from the fact that spin-orbit interaction been frequently computed through a solution of Dirac equation for moving electron. However, despite being calculated via the Dirac equation, the spin-orbit interaction is not a quantum mechanical effect. It is a relativistic effect as shown here. I will explain this fact. The Dirac equation can be solved in two ways, yielding identical result. In the first, it's solved in a static coordinate system for moving electron, where only the electrical field exists. Here, the spin-orbit interaction emerged directly within Dirac equation solution. The second method involves solving the Dirac equation in moving coordinate system for a static electron. In this scenario, both electrical and magnetic field exist, and both are considered. Since the electron is static in this case, the spin-orbit interaction arises not from the specific solution of the Dirac equation, but due to the presence of magnetic field in the moving coordinate system. As both solutions are the same, the spin-orbit interaction within the Dirac equation solution is essentially a magnetic field. This correlation of solution isn't surprising, given that both the Dirac equation and Maxwell equations maintaining invariance under relativistic transformations. Spin-orbit interaction can even manifest itself in macro world. For example, if the Sun were electrically charged, the Earth's magnetic field would align itself with the spin-orbit interaction's magnetic field created by this electrical charge. Also, magnetic field of the spin-orbit interaction in this specific example might be very small. It still exists. Next, I would like to discuss strengths of spin-orbit interaction. Typically, the spin-orbit interaction is very weak, as the formula for the magnetic field of spin-orbit interaction has the speed of light squared in the denominator. However, it becomes substantial when electron orbits an atomic nucleus, mainly due to two factors. Firstly, the electrical field near the nucleus is extremely strong. Secondly, the electron orbits at exceedingly high near-relativistic speed. For instance, the speed of an electron in the first orbital of hydrogen atom is 1/177th of the speed of light, indicating very fast movement. I am not saying that for non-orbital movements of electrons in some external electrical field, like this, there is no spin-orbit interaction. While spin-orbit interaction exists, in this case, it's notably small. All significant effects arising from spin-orbit interaction are attributed to the orbital movement of electron and electrical field of a nucleus. Examples of such substantial effects include magnetization alignment in a magnet, magnetic anisotropy, fine orbital structure, spin-dependent scattering, the spin Hall effect, and nearly all magnetotransport effects. The name spin-orbit interaction is historical but somewhat misleading, as it does not accurately represent the true nature of the effect. Spin-orbit interaction describes a magnetic field and has a distant relation to both spin and orbital moments. The only parameters of electron with which the magnetic field of spin-orbit interaction interacts is the spin. Due to its relativistic nature, this magnetic field does not interact with the magnetic moment arising from the orbital moment. Therefore, the inclusion of spin in the name might be partially justified. The relationship with the orbital moment is intricate. The presence of spin-orbit interaction requires the breaking of time universal symmetry, or T-symmetry in short. An electron orbital, when T-symmetry is broken, typically possesses a non-zero orbital moment. Therefore, the spin-orbit interaction has an indirect connection with orbital moment. Typically, the existence of the orbital moment implies the presence of spin-orbit interaction. However, this complex relationship can sometimes be disrupted. For instance, the most robust spin-orbit interaction is found in ferromagnetic metal, despite the localized electron within it typically having a quenched orbital moment, meaning orbital moment is zero. Next, I will discuss the importance of breaking time inverse symmetry, or T-symmetry, for existence of spin-orbit interaction. As I have just explained, sizable spin-orbit interaction occurs only during the orbital movement of electron around a nucleus. Observing 3D orbital movement closely, you will notice the electrons' equal movements in clockwise and counterclockwise directions. This 2D representation of orbital movements includes both clockwise and counterclockwise movements. For opposite movements, the direction of magnetic field of spin-orbit interaction is also opposite, as shown by green arrows. Consequently, this contribution balance each other, resulting in the electron experience no-net spin-orbit interaction. This is the case when T-symmetry is unbroken for the orbital movement. Reversing the flow direction of time implies an exchange between clockwise and counterclockwise movement, which in this case doesn't alter anything. For spin-orbit interaction to exist, there must be a distinction between clockwise and counterclockwise rotation, indicating the breaking of T-symmetry. This symmetry can be externally broken by applying a magnetic field, which creates the Lorentz force, shown by red arrows. Consequently, the Lorentz force affects the electron differently along its clockwise and counterclockwise paths. The force pushes the clockwise rotating part of electron wave function away from the nucleus, while drawing the counterclockwise rotating part closer to it. This creates a disparity in the electron field experienced by these two rotations. As a result, the equilibrium between opposing magnetic field of spin-orbit interaction is disrupted, leading to a significant magnetic field experienced by the electron, shown in the green. There are three possible methods to break T-symmetry. The first case involves unquenched orbital moment, which is a typical case for conduction electrons or band electrons. This interaction between the magnetic field of spin-orbit interaction and electron spins results in different energies for light Hall, heavy Hall, and split-off bands for valence electrons in a semiconductor. The second way to break T-symmetry is by applying an external magnetic field. This type of spin-orbit interaction is responsible for magnetization alignment in a magnet and magnetic anisotropy. The third method involves an electrical current. This type of spin-orbit interaction is responsible for spin-dependent scatterings, spin Hall effect, and most magnetotransport effects. It's crucial to note that T-symmetry cannot break on its own. It always requires some external breaking of the T-symmetry for the existence of spin-orbit interaction. This concludes part number 1. I will continue explaining the fundamentals of spin-orbit interaction in part number 2. You can find the link to that video in the description below this video.